Okay, moving on. I like to create this interaction diagram by setting up my spreadsheet term by term. Like I said before, we'll go through the main body of the diagram and then special conditions and limits to round it out. And remember that throughout, concrete has zero capacity and tension, only in compression. So the reinforcing steel will pick up the full tension load and some of the compression load, depending on its placement in our doubly reinforced concrete column. So in our case, our section looks like this, with reinforcing bar on the top and the bottom. And we have the section dimensions H and B with depth to the top and bottom rebar as well as clear cover. We'll take the reinforcing bar to be number 5 or 16 millimeter bar, and the stirrups or tie bars to be number 3, 10 millimeter bars. The strain diagram shows the top and bottom steel strains. Concrete compressive strain ECU, taken as the design maximum of 0.003, and C, our distance to the neutral axis. All these terms should look familiar so far. We are just adding a number 2 term or a second term to define this top steel, or D2, D top, and D1 is D bottom. So things are going to get a little more complex from what we talked about previously, because we are considering this top steel to be adding some capacity, usually in compression, but depending on that A value, that concrete compression block value, it can also be in tension. And then the force diagram shows A, which is the depth of the concrete compression section, as well as the steel tension or compression and the concrete compression. So to create the body of the diagram, we'll vary that C value from 0 to 30 centimeters. Any more, and we would just start to mirror ourselves. So this will fill out the main portion of the diagram, and then later we will back calculate C for four strain conditions that will give us our maximum and our minimum and round out all the rest of the points on the diagram. So A is the depth of the concrete compression block, or Whitney stress block, which we take as 85% of C. And the need for this 85% shape factor, reported as beta 1 in the code, is due to the variation in the shape of the stress strain curve for different concrete strengths. ES1 is the bottom strain steel, taken as C minus D1 over C times ECU, using those similar triangles that we talked about for calculating steel strain in a few lectures ago. And we'll let negative strain indicate tension, which makes sense here because ES1 will always be negative for C up to 30 centimeters because the full depth is 70 centimeters. Halfway is 35 centimeters, and we have our depth D2 reinforcing. That will make this always negative in that range. ES2 is the same as ES1, except we use D2, which is the distance to the top steel, or we can commonly refer to that as the compression steel as well. Now, for steel stress conditions, FS1 is the bottom steel stress, which will depend on the amount of strain, right? More strain is going to equal to more stress because the bar is getting stretched further. And if ES1 is greater than the yield stress of steel, which will take us 40 KSI, over the elastic modulus of 29,000 KSI, the max strain in the steel, we will take this as the limit stress of 40 KSI, which means the steel is yielding and it's not going to pull back, if you will, with any more stress than 40 KSI worth. If it's less, we will take this as ES1 multiplied by the elastic modulus to calculate the stress. Because we are under the yield stress or the elastic limit, we can assume that the steel stress varies linearly as a function of strain. So FS2 is the top steel stress and is similar. If ES2 is greater than the max strain, we'll take it as the limit, and if it's less, we'll have to calculate it, making that linear assumption again. Because the top steel can yield in tension and compression, we need to make sure to add a limit in both the positive and negative limit stress states. So you can see there's that extra term here where there's two terms here for Fy and negative Fy to define those limit states. And this is a lot of information. I'm just going through term by term, like I mentioned, how I would set this up in my spreadsheet. I would calculate each one of these terms out, break it down to as simple of equations as possible so you can see if anything's going wrong. And I'll show an example at the end, or I'll paste an example in here of how my table looks when it's done. So in the next lecture, I will continue going through some of these terms to create the main body of our interaction diagram.